Yeah, thank you very much. It's a pleasure to be here. I think this is the first talk that I've given here at the KGRC, so I'm very happy to be here. Also, I'm trying very hard not to have a cold right now, so hopefully my voice holds out until the end of the seminar, but you know, you'll have to bear with me, you know. And maybe I'll sit down and then someone else can finish my talk. So anyway, what I want to talk about today is something that you might describe as capturing by normal ultrapowers okay, and as I said, this is all joint work with Radek von Ziek. Okay, so let's get to it then. So in general, I want to fix a measurable cardinal kappa. So if I have a measurable cardinal kappa, I can take a normal measure on it, right? And okay, I take this normal measure, I can do the standard ultrapower construction. And what this gives me is an elementary embedding so I get J from V to M, where M is a reasonably nice model, right? So let's say M is closed under kappa sequences. Okay.
Can I ask historical questions? I forgot.
Yes.
Measurable cardinals were invented by Ulam, isn't that correct?
Yes.
Is it topological?
Was it topological? Was it combinatorial?
I thought they came up in topology, like everything.
They have.
So he was a set theorist.
Ulam was. Yeah. Well, you know, in the first half of the 20th century in Poland, you know, the boundaries of set theory and topology were blurry. So.
But this idea of this embedding, is this due to Dana Scott?
I think so. I would say so. Yeah. So.
I think Ulam proved that one is not measurable, or something like that, right? Oh, okay. So,
the Ulam matrix.
The Ulam matrix. Okay. So he knew what cardinals were not measurable. So I mean that's.
He was a visiting professor at MIT for a semester.
Oh really?
His office is down the hall from me. I met him.
Oh yeah.
I don't remember anything. I never discussed Ulam.
He also worked on the Manhattan Project, I think.
Yes.
Oh really?
Applied set theory.
Applied set theory. He used the measurable cardinal as the ignition point.
Okay, sorry for the interruption.
No, not at all. Okay, so I get this embedding. M is quite a nice model, and of course the critical point of J is kappa, so the first ordinal move by J is kappa. Okay, so then there's a kind of picture here that we can look at, right? So first there's a V because, you know, every picture in set theory looks like this. And then there's a J. And then, okay, then I have a model on this side, right? So I have to start drawing M. So what does the fact that M is closed under kappa sequences tell me? Well, if kappa is here, then M up to kappa will look just like V up to kappa, essentially, right? So it picks up everything. Okay, and okay, depending on how I index this, maybe up to kappa plus 1 even. Okay, you want to think of this as V kappa plus 1 and V kappa plus 1 in the sense of M. Both of these are just the same because essentially this is just the power set of kappa. Okay, but what happens afterwards is that M suddenly becomes more fit or trim or whatever you want to say, you know, less flabby than V. Somehow it thins out, okay? And the general idea here is that above kappa plus 1, sets start missing from M, okay? So it will, in general, if I compute V kappa plus 2 in the sense of M, this will be incorrect. So it will be different from the real V kappa plus 2. Okay, and we have a canonical example for.
Wait, what you wrote is a logical.
No, M, the M belongs to the picture. The second M.
Oh, this M. There we go. There we go. Yes. Everything I write is correct for an appropriate value of correct. For mod finitely many errors, everything I say is correct. So we have a canonical example for this incorrectness, right? So it's fairly easy to see that the measure U itself, by which I took this ultrapower, so U itself is not an element of M, okay? And this is not hard at all to see, right? If you haven't seen this, what would happen if U was in here? Well, if U was in M, then M could compute its own ultrapower by U, okay? But because M is closed under a lot of sequences, then the initial part of that ultrapower would be the same whether you compute it over M or compute it over V, and then M would see that J of kappa is an accessible cardinal, which contradicts the fact that by elementarity J of kappa is supposed to be inaccessible in M. Okay, so we have this example of incorrectness at sort of the first possible level that can happen, the V kappa plus 2. Okay, so, you know, if GCH holds, okay, this essentially tells us, in other words, that the power set of kappa plus of M is incorrect, because V kappa plus 2 is essentially coded by the power set of kappa plus. Okay? But, on the other hand, if GCH fails, then this kind of coding doesn't make sense anymore. Okay? And you can ask the question, could this ultrapower M compute more power sets correctly than just the power set of kappa? Okay? So, this was a question asked by Steele in, let's say, 93. So is it consistent that there is some normal ultrapower at kappa that computes the power set of kappa plus correctly. Okay? Okay, so this is a perfectly good question. There's an easier version of this question that you might want to tackle first. A weaker version. Which wasn't asked by Steele, but I think makes sense. So, is it consistent? So, instead of requiring that there's a normal ultrapower that computes all of the power set of kappa plus correctly, maybe I'm just interested in asking the question, can any subset of kappa plus be found in a normal ultrapower like this? Okay, so instead of asking for one uniform witness for this kind of capturing phenomenon, I just want to ask the question for each set at a time. So is it consistent that for for any x subset kappa plus, there is a normal ultrapower m at kappa such that x appears in this m. Okay. So obviously, okay, if I answer yes to this, then I answer yes to this.
This might have weaker consistency.
This might have weaker consistency strength, yes, yes, yes. Okay, so these are sort of the two questions that I want to think about, so these questions were answered, you know, before I reached mathematical maturity. But you know, these will be the guiding questions for this talk. So let's just introduce some terminology so that we have, so that I don't have to keep writing all of these words down. So let's say definition. So kappa measurable, x a set. Okay, we're going to say that a normal measure u on kappa, or its ultrapower m. So I'm going to use the same term for measures and ultrapowers. So we say that the measure captures x if this thing happens, if x appears in that ultrapower. Okay. Okay, and then I'm going to define two properties that kappa might have. So let's say kappa less than lambda cardinals. Okay, and then we're going to say LCP kappa lambda holds. LCP stands for local capturing property. If for any x subset lambda, there is a normal measure on kappa that captures x. Okay, so this is the local capturing property, one set at a time. And then if I get rid of the local, CP kappa lambda says that not each set separately, but the entire power set of lambda is captured by some ultrapower at kappa. Okay.
There's a question. Is normal
Yes.
relevant here? If you normalize the measure, does it change?
So normal is relevant because, let's see, if I have just any embedding that captures a lot of things, but it's not necessarily normal ultrapower, then there's the typical way of factoring out the normal ultrapower. And then instead of just factoring out the normal ultrapower, I could throw in any subset of, say, kappa plus, and it would survive. So, you know, as I factor it out, it wouldn't collapse in any way. So that subset of kappa plus would be captured by some ultrapower in kappa, but not necessarily a normal one. Okay, so to make this question less trivial, I want to focus on normal ultrapowers, because if I allow any kind of ultrapower, then I can combine things in such a way that I can make more or less anything that I want appear there. What was the question?
Does it make a
Does it make a
difference?
difference? Yes.
Right, yes, it makes a difference, yeah.
I was listening.
It's very good. At least someone was. Okay, so I guess before I move on, so in other words, what Steele's question was, is the capturing property kappa kappa plus consistent? This weaker version is the local capturing property kappa kappa plus consistent? Okay, and if it is, what can you say about it, and so on and so on. Okay. I see. Now I have to figure this out. We'll see. We'll see what you say after it dries. This is a very European way of cleaning blackboards, so my grad school days did not prepare me for this, but well, yeah. Anyway, so looking at these questions, okay. So what has been said, okay? So for Steele's question, Cummings gave an answer. Okay, so we have a theorem. This is Cummings. This is also 93. This is one of those strange situations where the answer appeared before the question appeared in print. So I don't know what that means for causality and things like that, but anyway. So what Cummings proved is that if kappa is kappa plus 2 strong, then in a forcing extension, CP kappa kappa plus holds. And if you're worried, the forcing extension preserves kappa plus, so there's no ambiguity what I mean by this. And moreover, I should say this, moreover, the hypothesis is optimal. Okay, so if you have a kappa plus 2 strong, you can force to get this capturing property, and if you have this capturing property, then kappa is kappa plus 2 strong in an inner model. I should point out that it's not surprising that I need non-trivial large cardinals to get this, right? Because we said before, if GCH holds, then there's no way that a normal ultrapower can capture all of the power set of kappa plus, okay? So definitely if I want the capturing property at kappa kappa plus, I'm going to need to make GCH fail at kappa, okay? And we know by results of Giddick that I definitely need, well,
kappa's kappa plus.
Right, I definitely need more than just a measurable to even get the cardinal arithmetic to work out properly. So if I have GCH, then at kappa, right? So I don't care about general, but at kappa I need 2 to the kappa is kappa plus. Okay, so I definitely need more than just a measurable to make this true, okay? And this kappa plus 2 strong is just a smidge over what I need just for the cardinal arithmetic. Okay, so this is just slightly above O of kappa is kappa double plus. Okay, on the other hand, before I move on to that, if I ask this weaker version of the question, it's not immediately obvious that this is in any way related to the GCH. Okay, a priori, it seems completely plausible that any subset of 2 to the kappa separately could be captured by some normal ultrapower.
But I still fail to see why the other thing is related to it.
Because 2 to the kappa is not kappa, because of the ultrafilter.
Right. If 2 to the kappa is kappa plus, then the ultrafilter is coded by a subset of kappa plus. Yes.
So basically CP kappa 2 to the kappa doesn't.
CP kappa 2 to the kappa fails, exactly. Yeah.
You
So
would need more than one ultrafilter on kappa to get the local version.
what do you mean?
You need more than one ultrafilter on. Assume you need more than one ultrafilter.
You see more
Local but not global. You need more.
You need more than one ultrafilter. Yes, exactly. Yes.
So having just a measurable is certainly not enough.
Yes.
Because there could be
Yes.
only one.
Exactly. Yes. Yes. That's very true. Okay.
So more is
The consistency is strength of having many, it's the same as consistency strength of having one. So,
That's true. But I'm going to sketch for you that I actually need more than just a measurable. So, but a priori, what do you want? Okay, so let's focus for a minute, and by a minute I mean more than 1 minute. So, on the local version. Okay, what can you say about this? Okay. Okay, we observed that CP kappa 2 to the kappa fails. Conceivably, LCP kappa 2 to the kappa is still plausible, but even one step more also fails. So LCP kappa 2 to the kappa plus fails. Okay. So we might be able to locally capture a bit more than globally capture, but already at the next step we fall down. Okay, why is this true? Let's see. Well, if this held, okay, what is a interesting subset of 2 to the kappa plus that I can capture? For example, I can make a normal ultrapower that is correct about all the cardinals up to 2 to the kappa plus, right? Because I can throw in all of the witnesses that something below 2 to the kappa plus is not a cardinal. Okay, then there is a normal ultrapower. Let's call it J from V to M, such that M computes cardinals up to and including 2 to the kappa plus correctly. Okay, but this is already problematic, right? Because look at J of kappa and look at J of kappa plus. Okay, both of these are cardinals in M. They're different, but if you compute their sizes in V, right, both of these have size 2 to the kappa in V, right? So are both ordinals of size 2 to the kappa in V, but are cardinals in M. Okay, and this gives me my contradiction, right? Because, either M is correct or V is correct, but they both can't be correct. Okay, so we have an upper bound for when LCP has to fail. Okay, but maybe we can see if this is optimal in any way. Okay, so let's try to get the best alternative. So let's try to get LCP kappa 2 to the kappa. Okay. So there's a very old fact in the background here, which I think is due to Solovey. So let's see. If kappa is 2 to the kappa supercompact, and I don't even need this, so I'm just going to say, or just kappa plus 2 strong. You know, I'm hedging a lot here. Then LCP kappa 2 to the kappa holds. Okay. So this is, okay, I say 2 to the kappa supercompact because I want to sketch the proof using the supercompact one. But, you know, if you can think about the strong version, it's not, you know, different in any significant way. So how does one see this? Okay, let's say that I have this 2 to the kappa supercompact embedding, right? So M is very, very, very closed. Okay, and let's assume LCP kappa 2 to the kappa fails. Yeah? Okay. Now, because M agrees quite a lot with V, M will also think that LCP kappa 2 to the kappa fails. Okay, because it can compute all of the same measures as V can and all of the same sets and so on and so forth. Okay, now look at this. So now I'm going to factor out the normal measure from this embedding. Okay, you can compute in your own time the critical point of K, this factor embedding, is strictly above 2 to the kappa in M. Okay. In particular, what this means is that because M thinks that LCP kappa 2 to the kappa fails, N will also think that LCP kappa 2 to the kappa fails. Okay. Because 2 to the kappa is not moved between N and M. Okay. So N thinks LCP kappa 2 to the kappa fails. Okay, so N has a witness for that. N has a subset of 2 to the kappa that is not captured by any measure. Okay, so take some X in N, a counterexample. Okay. But then just follow this X back, right? This X does not move when mapped by K, so therefore M also thinks that this X is a counterexample to LCP. And because M and V agree quite a lot, V will also think that X is a counterexample to LCP. Okay, but this is nonsense because clearly X was captured by M. Okay, so therefore V at the outset must actually believe that LCP kappa 2 kappa is true. If you go one step further, you can actually see that not only does V think that LCP kappa 2 to the kappa holds, but M will also think that LCP kappa 2 to the kappa holds, right? Because again, M and V agree quite a lot. Okay. What this means, reflecting back to V again, is that okay, if kappa is 2 to the kappa supercompact, or just this strong thing, it has many kappa primes below that also satisfy LCP kappa prime 2 to the kappa prime. Okay, so if nothing else, I know that these large cardinals are overshooting the consistency strength of LCP kappa to the kappa. Okay, so let's try to get a more precise bound on the consistency strength. So I'm going to very quickly recall what the Mitchell order is, just so that we know what's happening. Okay, so recall the Mitchell order. On normal measures. Okay, so if I have two normal measures, U and V, both living on kappa, we're going to say that U is Mitchell below V if, if U appears in the ultrapower by V. Okay? So it's somehow measuring the fatness of the measures. Okay, V is much more rich than U because U itself appears in the ultrapower by V and so on. If you think about it, having a measurable with measures that are ordered like this, so with a non-trivial comparison between measures, already means that, say, kappa cannot be the least measurable, right? Because U is in this ultrapower, therefore kappa is measurable in this ultrapower, and then by reflection, again, there are many things in V below kappa that are also measurable. Okay, so having non-trivial Mitchell comparisons pushes me way beyond, the first measurable or something like that. Okay, I should say, so I have this ordering. This, you can check that this is a well-founded partial ordering. Okay, and therefore it has a rank function. And so and then O of kappa, the Mitchell rank of kappa is just the height of this ordering on the normal measures in kappa. Okay.
But it's not linear.
It's not linear.
Well-founded partial.
It's a well-founded partial order. Okay. Another thing you can check and think about is that O of kappa, there's an upper bound for what O of kappa could be. So O of kappa is always less than 2 to the kappa plus. Okay. And you can think about this just based on how many measures could possibly appear in a normal ultrapower like this. And it turns out that it's not that many. Okay. Ugh. Okay, so let's see. So let's see now that LCP actually gives us some consistency strength. So let's call this a proposition because it's not very hard. LCP kappa to the kappa implies O of kappa is 2 to the kappa plus. Okay, so this local capturing property already implies that the Mitchell rank of kappa is as large as it could possibly be. Okay, now if you know how to prove from those large cardinals up there that the Mitchell rank of kappa has to be big, so if you know how to prove that A 2 to the kappa supercompact cardinal has large Mitchell rank, or a kappa plus 2 strong cardinal has large Mitchell rank. The proof of that factors through this proposition, essentially, or through this sketch and through this proposition, right? So how do you see this? Well, you just build a Mitchell increasing chain by induction, right? So I'm going to start with one measure, okay? This measure is essentially a subset of 2 to the kappa. So applying LCP kappa 2 to the kappa, I can capture this measure by some other normal measure, okay? So therefore, that capturing measure is Mitchell above the first one, okay? And now I can move on. Now I have these two normal measures. Both of these together are coded by a single subset 2 to the kappa, so I can find another one that sits above both of them, okay? And I can go on and on and on. And as long as I have, at most 2 to the kappa many things in my chain, I can put them all together, code them by a single subset of 2 to the kappa, and put another measure on top using LCP kappa 2 to the kappa, okay? So the induction goes up to 2 to the kappa plus. Okay, I just capture all the initial segments of my chain and I put something on top. Okay, so I definitely know that I'm going to need more than just a measurable to get this LCP. Okay, but in fact, we can also convince ourselves that a large Mitchell rank is sufficient to get kappa with this local capturing property. So we're going to capture the consistency strength of this LCP exactly. Okay. So here's a theorem, which I may or may not actually prove. So we'll see. So let's see. Let's assume that O of kappa is kappa double plus. Is at least kappa double plus. Okay, then LCP, let's say it like this. LCP kappa plus holds in an inner model of GCH. Okay. So it's sort of ambiguous how to phrase this. I could, I want to say this is enough to get me a model of LCP kappa 2 to the kappa, but, then I have to be careful where I compute 2 to the kappa, okay? So what I'm saying here is, as if you give me a cardinal of high Mitchell rank, then I can give you a model where LCP kappa 2 to the kappa properly interpreted is true, okay? And therefore, the consistency strength of this local capturing property, the best local capturing property that you can hope for is exactly, let's say O of kappa is kappa double plus. Yeah.
Can you also do the same with kappa double plus? And not GCH, but...
I see. Yes.
Kappa double plus in a model of almost GCH.
You're going to need
so
high order.
Assume you have kappa triple plus.
Right. So I'm going to have to do some forcing to make GCH fail, right? I'm not going to be able to just go to inner models, probably, right? Because if I want LCP kappa double plus and GCH,
kappa is kappa double plus and order of kappa is kappa triple.
Right. Right. So I'm not going to be able to go to an inner model, but I will be able to force something like this. Oh. Right. From appropriate hypotheses, more than this.
You want to catch subsets of kappa doubles, so you're going to have to use extenders.
Yeah.
And
Yes.
order kappa double plus
Yes.
plus.
Yes. Yes. Yes.
For measures.
Yeah, exactly. So maybe let me not go into the proof of this, but if you're familiar at all with inner models of cardinals like this, then this should be not very hard, right? So if I start with this, I can move to the Mitchell model L of U vector for this, okay, and then I can prove that in L of U vector LCP kappa kappa plus holds, just by proving that in that model any subset of kappa plus is constructed from some proper initial segment of the sequence of measures, and therefore it's captured by some normal ultrapower. Vaguely speaking, yeah. But let's not dwell too much on this because I want to move on to the global version, not to the local version.
That's how you prove it. I don't see how you're going to prove something like Martin said with forcing and then just get local capture in an extension where to the kappa.
I'm going to get full capturing. So I'll be able to start with something more than this, and I'm going to get full capturing property kappa double plus if you want.
What's the consistency strength of just the local?
I see. Right. I see what you mean. Okay. I'm going to sort of give an answer off the top of my head, but I'm going to say that if you want LCP kappa double plus here, you will probably want something like O of kappa is kappa triple plus but not for measures, but now for extenders. Yeah, something like that. Okay. So before I move on to the global version, I want to pose a question that I don't know how to answer, but if you find this talk boring, then maybe you can think about the question and tell me afterwards. So here's a question. So what did we do up there, right? We proved that if kappa is quite large, then LCP kappa 2 to the kappa holds. Okay, so if kappa is 2 to the kappa supercompact. And in fact, to run this argument, we needed full 2 to the kappa supercompactness because all of the sorts of reflection of LCP going on between this model and this model and this model needed that all the measures were computed the same between V and M and so on and so forth. Okay, so it's unclear whether if I started with less supercompactness, I could still recover some amount of local capturing. Okay, so I'm going to pose a simple version of this question. So suppose 2 to the kappa is kappa double plus, and kappa is kappa plus supercompact. Okay, does LCP kappa plus hold? Okay. So kappa is kappa plus supercompact. So there is some embedding that captures whatever subset of kappa plus I want. Is there a normal ultrapower that captures that set? I don't know. Okay. So this is one question. So this is sort of the question that gets raised by this argument. There's another question that gets raised by this argument. So this is maybe question 1. Question 2. Again, this argument told us if I have a lot of local capturing all the way up to 2 to the kappa, then I get large Mitchell rank. Okay. What if I have slightly less local capturing? Does that still give me some non-trivial Mitchell rank? Okay. Again, this proof doesn't seem to go through because you know, to build even this first step, I wanted to capture this measure, and this is a subset of 2 to the kappa, and so on and so forth. So what can I do? Okay, so the question is, again, maybe suppose 2 to the kappa is kappa double plus, and LCP kappa plus holds. Okay. Does kappa have non-trivial Mitchell rank, for example? Yeah? Okay. I don't even care as much about saying, okay, maybe it has, oh, if kappa is kappa plus or kappa or something, you know. Does it have non-trivial Mitchell rank at all? Okay.
Well, maybe this is trivial. Can you have a normal measure? Can you have 2 to the kappa bigger than kappa plus, and the normal measure generated by kappa plus many sets? Or is it impossible?
That seems implausible to me, but
Isn't that U of kappa?
Yes, is
U
U
of
of
kappa.
kappa, does U of kappa have
Yeah.
to be continuum?
So with supercompactness, you can do this, right?
well, but
U of kappa to the kappa
Yes.
plus. and
well, but is it a normal one? Do you get?
Yeah.
I mean, yeah. Okay.
I mean, it's not easy, but you can do it.
I see from large.
Probably due to Salah and Jamoni.
Okay. 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 So I don't know how to answer the first question. I will tell you how to answer the second question. Okay. So the answer here is no. Okay. And this is what we're going to move on to. Just make space for myself.
But in question two, in the inner model, it should have no Mitchell rank.
In an inner model, yes.
The core model,
Yes. Yes.
you say that V is not.
Yes. Yes. But not in V is the point.
Consistency strength.
The consistency strength will still be large. Yes. But not necessarily in V. Yes.
Kappa double plus.
Kappa double plus. Yes. Okay. So this is the theorem. That we can do. So starting from, again, the same hypotheses that Cummings did. So if kappa is kappa plus 2 strong, then in a forcing extension, CP, so not just local capturing, but full capturing kappa plus holds, and kappa is the least measurable. Okay. So not only does it have trivial Mitchell rank, it's the least one. Okay. Okay. So I want to spend, I guess, the rest of my time telling you something about how you prove something like this. But in order to put everything into context, I need to tell you something about Cummings' original proof of sort of, he proved essentially this without this last and clause. Okay. So how did Cummings argue. Okay.
Don't you want to assume GCH in the ground model before you start?
I can force GCH.
What's going to happen to the strength? Dangerous, right?
Well, I don't think so, because I mean this is already kind of immune to the GCH because, you know, kappa plus 2. I'm not saying that I'm capturing, you know, h of kappa double plus or something like this. I'm capturing all of v kappa plus 2, right? So if I force GCH, I don't think I break this at all.
All right.
Yeah. But if you want, you can throw in GCH to start with, you know. Okay, so how did Cummings do this? So, okay, step 1. What is step 1? So, okay, you have this strong cardinal. Okay, so you start with a fat embedding. You know, that definitely captures everything you want to capture at the end of the day, right? So it captures the entire power set of kappa plus. Okay, but is not itself necessarily a normal ultra power by measuring kappa. Okay, so this comes from my strongness hypothesis. Okay, then you sort of look at the situation and you say, well, definitely I'm going to have to force GCH to fail. So I'm going to have to force maybe 2 to the kappa is kappa double plus. So let's do that first, and then, you know, we'll deal with everything else later. So force. Okay, because this is just necessary to have that capturing property. Okay, so I force this and I lift J, yeah, with some technology. Okay, and then step 3 is essentially you hope that everything worked out, you know, so hope. You know, you don't really know what to do after this point anymore, but, you know, magically things will work out. And the real magic is contained in the key observation. So what is going to happen here is that I have my fat embedding. I'm going to force through the kappa is kappa double plus. I'm going to lift this embedding. And then magically, this lifted embedding will just be a normal ultra power. Okay. Suddenly, it didn't used to be, but now it will. Okay. So we're going to phrase this in very learned language. So suppose J from V to M is a kappa lambda extender embedding. And 2 to the kappa is at least lambda. Okay. If you don't know what a kappa lambda extender embedding, you'll see what it is in the proof. It's nothing very fancy. So if 2 to the kappa is at least lambda, then J is just a normal ultra power at kappa. Okay. So just by ensuring this, you know, absolutely necessary fact about numerology in the model, my embedding that I had from before is going to turn into a normal ultra power and give me everything that I ever wanted in life. Okay. Let's see. So suppose I have this J from V to M, that's a kappa lambda extender map. Okay, and what that just means is that M, so every element of M has a particular form. So everything in M looks like J of F of alpha, where F is some function with domain kappa, and alpha is less than lambda. Yeah. Okay, this is all that it means, or what I want it to mean right now. Okay. So I have this embedding, and again, I just pulled the same trick I did before. I factor out the normal ultrapower, and look at this factor map, K. Okay. And now I'm going to look at this K, and I'm just going to prove that it's an isomorphism. Okay, and in fact, not just an isomorphism, it's the identity. Okay, and so this map J is just equal to the map I. Okay, so why is this true? I mean, you know, ostensibly, the slogan is, well, the critical point of K is very high, so it doesn't move any of the generators of this extender, right? But speaking more formally, right? So K is surjective. Why is that true? Well, if I look at J of F of alpha, some element of M, I can write this as K of I of F of alpha, right? Because this diagram commutes. Because alpha is less than 2 to the kappa, it's below the critical point of K. So alpha is just equal to K of alpha. Okay, and then I just apply elementarity of K to get that this arbitrary element of M is just equal to K of I of F of alpha. And therefore, K is surjective. Okay? And so K is surjective, obviously it's injective, so it's an isomorphism, but because both of these two structures are transitive, it has to be the identity. Okay? And this tells me that this embedding I have at the top is just this normal ultrapower that I have here. Okay.
There must have been more to Cummings there than this.
Well, I mean, there's more to Cummings because he has to arrange this in a reasonable way. Okay, but this is sort of a key observation that needs to happen.
Start with the extender ultrapower representation,
Mm-hmm.
and we'll have that after.
Yeah.
After four, so.
Yeah. So I mean, really, the hard work is in step. Yeah, the hard work is in step 2 here. Yeah. You know, but we can debate what the hard work is with the benefit of hindsight. It's.
Okay, I'm not going to argue about it.
No, sure, yeah. Well, it was. I mean, this is the early 90s. You know, all of these things were quite new around that time, right? Okay. So this is how Cummings argued, and we want to do something building on this construction, okay, but somehow incorporating making kappa the least measurable at the end, okay? So there's a few ways that you can think of trying to do this, okay? So the first thing you would think of is to say, okay, take this model of the capturing property that Cummings produced, okay, and then just force over this model to make kappa the least measurable. You know, that's a fair enough idea, okay? And then hope that, you know, you have this capturing map in your model, this J, and then hope that that J somehow gets preserved to the extension that makes kappa the least measurable and that everything is fine, okay? You're going to have serious problems with trying to make this work because the usual machinery that makes kappa into the least measurable, you know, either iterated prick reinforcing or, you know, adding non-reflecting stationary sets or something like this, you know, in order to preserve measurability or some kind of measurability, you want to start with embeddings or measures that are very impoverished. You tend to want to start with Mitchell minimal measures and then preserve fragments of that to the extension where kappa is the least measurable. Okay, so if I start with just an arbitrary embedding that captures the entire power set of kappa plus, there's no reason for me to expect that anything of that embedding will get preserved to the forcing extension where I make kappa the least measurable. Okay, so maybe I can't just do this first and then make kappa the least measurable on top of that. So I'll kind of have to do this and make kappa the least measurable at the same time. Okay, so I'm going to do some iteration where I'm going to blow up in the continuum function and also kill measurables below kappa at the same time. But if you think about this, you sort of realize very quickly that when you kill measurables below kappa, you better not do it with objects of size kappa plus. Okay, and why is that? Well, let me just put this here for a second, right? So suppose I have V or VG or something, okay, where kappa is the least measurable, but there's this J here into M, and the entire power set of kappa plus appears here, okay? But let's say that I killed the measurables below kappa coming from some ground model in a way that used objects of size, to kill gamma, I use an object of size gamma plus, okay? So if I want to make any kind of lifting machinery work, then I'm going to have this J, and on the M side, the measurability of kappa will be killed by an object of size kappa plus, right? Okay. But look, on the V side, kappa is still measurable, right? So the thing that killed the measurability of kappa in M must itself be killed. Okay, and if the thing over here had size kappa plus, then probably it has the thing that resurrected kappa probably also has size kappa plus. But then that thing that resurrected kappa must also appear here. So kappa must also be resurrected on the M side. Okay, there's too much agreement between V and M if you have capturing for kappa plus to kill measurability with sort of puny objects of size kappa plus. Okay. So you sort of realize that you're going to have to do this and kill measurables below kappa with huge objects. Okay.
Oh, wait, how did it get huge? You said bigger than gamma plus.
I mean huge in the non-technical sense. I mean, okay, gamma double plus is quite huge.
It's huge.
It's quite huge. Yeah. Okay, so let's see how one does this. So to do this, I want to present, I hesitate to say an obscure forcing notion, but I would argue it's not very well known, that is going to kill a measurable cardinal, say gamma, while at the same time blowing up 2 to the gamma to be gamma double plus. Oops. And it's going to do it in a way that's resurrectable. So, undoable. Okay. So we're going to use the forcing due to Apter and Scheller. Okay. So fix, let's say gamma is inaccessible. Yeah? Then I'm going to define, well, I need to fix more things, don't I? Okay. So I'm going to fix gamma inaccessible. I'm going to take an I, some kind of index set of ordinals below gamma double plus of cofinality omega. Okay. and I want to fix a ladder system on I. Okay, so with this, so each x alpha is just a cofinal omega sequence in alpha. Yeah? Okay, so I'm going to define a forcing. So let's call it A gamma double plus and X. Okay, so conditions are going to be pairs, so let's call it PZ. And let's see, so the working part P will be just a Cohen condition in add gamma double plus. And to make my life easier, I'm going to insist that this Cohen condition is uniform, which means that all of its non-empty columns have the same height. Okay. The side condition Z will be a subset of the ladder system. So it'll just pick out some of the ladders. And I want to insist that for every ladder in Z, I'm only allowed to pick ladders that live in the support of my working part. So X alpha should be a subset of the support of P. So I'm only allowed to pick ladders above which I've already, my working part already says something.
And supports of size less than gamma.
Supports of size less than gamma, yes. Yes. So I didn't explicitly put any bounds on the size of Z, but it follows from this that it has size less than gamma. Okay, so these are the conditions. How do you order them? Let's see, so we're going to do PZ is stronger than P prime Z prime if, okay, there's some obvious ones, so the working parts should strengthen, the side conditions should get bigger. Okay, and now I need to actually use the side condition. Okay, so let me draw a picture of a condition so that we know what's going on. So here's gamma double plus, okay, and the working part filled in some stuff here maybe, and maybe later, okay. So this is my working part, and then the side condition picks maybe one ladder. I don't know, it picks many, but let's focus on one ladder. So it picks some of the columns, maybe this one, maybe this one, maybe this one, and so on, you know, omega many columns for each ladder. What is the side condition telling me? The side condition is a promise that whenever I strengthen the condition, the columns that I picked out will never again have an element in common. Okay, so the intersection of the generic sets added by these columns will be bounded by this height of the working part. Okay, I'm going to require a bit more, not just that the intersection of these columns is bounded, but also the intersection of their complements is bounded. So I just make sure that, you know, these countably many columns never get another thing in common. So what do I need to write? So for any, let's see, X alpha in Z prime, if I look at the part of, so the new part in the working part, so P minus P prime, and I restrict it to this ladder X alpha, okay? This thing, how do I want to say this? Okay, this thing has infinitely many zeros and ones in each row. Yeah?
So you have P minus P prime and then evaluate it at alpha? Or
So P minus P prime, so this is the new part, and then look at it restricted to this ladder. So look at these infinitely many columns that the ladder picks out.
the ladder is a subset of alpha.
The ladder is a subset of alpha, yes.
And you look at the ladder lives at a, I mean, the condition is a partial function from gamma. No,
From gamma cross gamma
into 0, 1.
double plus into 0, 1, yes.
And so you look at the condition at a coordinate in gamma double plus.
I look at a condition restricted to countably many coordinates in gamma double plus.
Oh, restricted to.
Restricted to, yes. Yes,
Of course.
yes,
Coordinates on the ladder.
yes.
Coordinates of the
So what's
ladder
a
and
column? It's when,
So-
a row, I mean, it's something that goes like this.
A row is something that goes like this, right?
It has infinite many zeros and ones, does not seem like a very strong. What does that do with being disjoint? That just is-
Well, if you think of what is each of these columns is going to grow into a subset of gamma, right? So if I have, forget about the infinitely many, just say that each row here has at least one 0. Okay, that means that if I intersect the sets coming from these columns,
All of them, not pairwise.
all of them, yes, all of them, yes, yes, all of them. Okay, so what I'm adding with this forcing is some kind of almost disjoint family in a weak sense. It's not pairwise almost disjoint, but some infinite subcollections will have bounded intersection. Okay. I want to observe something. So sometimes this won't be very interesting, okay? So for example, if I pick my ladder system very, very poorly, this won't be very interesting, right? So if the ladders are pairwise disjoint, okay, then I'm just doing something very, very silly, right? Then there's no interaction really between the different elements of the side condition. Okay, so I can split this forcing up into, you know, columns that live above some side condition, columns that live above some other ladder, and so on and so on. And each one of these will just look just like plain Cohen forcing. Okay, so if everything splits up nicely like this, then this is just plain Cohen forcing. Yeah. Okay. And in fact, I don't even need them to be completely pairwise disjoint. It's good enough if they're essentially disjoint, which is a term I learned from Daniel a few days ago. So it's good enough if just I can cut away finitely many points from each ladder, and then I get something that's pairwise disjoint. Okay, then it is still true that this is just plain old Cohen forcing. Okay, so to make this interesting, I better pick my ladder system to be interesting. Each X alpha has order type omega.
any two are, but you want to.
Any two.
What is I? The index set is I. What does it require the index set I?
So I haven't required anything yet, but to make this interesting, I'm going
That's
to.
discrete, then.
Right, exactly. Right, yeah. So I'm going to have to require
It's not going
something.
to be gamma double.
It's not going to be gamma double plus. Okay. So let's see. What else can we say? So I'm going to, in the interest of saving some time, I'm going to just list some properties that I want both the ladder system and the index set I to have, so that we get to where we want to be. Okay, so in practice, we want I, so I is still here, but now I want it to be a non-reflecting stationary set. Okay. So I want I to be this, and X is a, okay, let's see, is a club I sequence. Okay. So what is a club I sequence? It's a ladder system like this, and it has a relatively nice guessing property, which tells you that for any unbounded subset of gamma double plus, there's one index alpha, so that X alpha is a subset of your set. Okay. You can say one, you can say stationarily many. We're going to need just one. Okay. So let's see. Some properties of this forcing. Assuming now that X was chosen to be like this, to be this club sequence. Okay. So let's see. You can check that it's less than gamma closed. You can check that it's gamma plus Knaster. Okay, none of this is very hard. You can also check that it forces 2 to the gamma is gamma double plus.
That means for every subset of size gamma plus, there's a subset of
Yes.
that,
Which is linked, which is pairwise. Yes. Okay. So you can check that it actually does add gamma double plus many new subsets to gamma, which you would expect that it does, but it's not completely obvious from, because, you know, how do you normally prove this? Well, you say, give me a condition, can I add 1 bit to it? But maybe the side conditions are so intertwined that I can't, you know, add 1 bit without messing up something else. Okay. What saves me here is this non-reflecting part, which lets me sort of unbounded parts of gamma double plus work the way I want to work. So this is one property. The second property, okay. And then the third property, let's see. A gamma double plus X kills the measurability of gamma. Okay. So let me tell you very, very briefly why this should be the case, because it's a slightly weird argument. Okay. So sketch. Okay, so I'm going to take a condition, and I'm going to take a name for a measure on gamma. Okay. Okay.
Yeah, also then won't you have to show somehow that no gamma plus size subset of it already kills the measurement?
So let's see. I can show that any sized gamma plus subset of it is just a plain Cohen extension or something like that. So it should be safe. But yeah, that's a good point. Okay, so take a condition, take a name for a measure on gamma. Okay. So now for every column, right, so for every I can find a stronger condition Pi Zi that decides the ith set into U or not into U. Okay? So now I have gamma double plus many conditions. Okay? I can use knasterness to refine this to still gamma double plus many compatible conditions, and I can sort of assume that all of them decide their sets into U if I want. Okay, so assume we have many pairwise compatible I that decide the same way. Okay, so ideally what I would now want is to take maybe countably many of these, okay, put them together, get a stronger condition, and then take those countably many and stick the collection of indices into the side condition. Okay, so what will that do for me is, well, all of the countably many together will force that these countably many all got into the measure, but the side condition will force me to prevent those countably many new sets from getting into the measure. Okay, I can't necessarily do this a priori, but because my ladder system was a club sequence, I can take these many indices that I have from here, and I can find a ladder that gets inside the set of indices.
Why does the side condition prevent that it's
So the side condition tells me that however I strengthen the intersection of these countably many sets that are ostensibly in the measure is small, right? But because if the measure is complete, then the intersection would have to be large. Okay, so we use this to find an extension that prevents countably many sets. Well, that makes countably many measure one sets have bounded intersection.
An extension means for each pi in the extension.
No, so it means you have a lot of PIs, use this club sequence to find countably many of them, and then argue that these countably many have a common extension.
But the set was only linked.
The set was only linked, so I should have said something stronger here. Yeah, I can get a stronger omega 1 linked. Yeah.
Or
yeah, I can get a stronger length property. Okay, and this gives me a contradiction. Okay. So the final thing I need to tell you, well, I need to tell you two things, right? First of all, I need to tell you where in the world these club sequences come from. Okay. And second of all, I need to tell you, well, you killed the measurability of gamma. Okay. How do you resurrect it now? You know?
Resurrect means you want the kappa is measurable.
I want that, well, any particular gamma can be resurrected, but in the end, I'm going to resurrect kappa. Yeah. So, I mean, the result is general, so that, you know, if gamma started out being measurable, then I can do some forcing on top of this to recover the measurability of gamma. But I'm going to use, in practice, I'm going to use this at kappa. Okay, so I'm going to tell you first things first. So where does this okay, and the point is, the standard forcing to add a non-reflecting stationary set, I like this, will just by itself add a club sequence like this as well. Okay, so if I just force to add this non-reflecting stationary set, I'm going to get this club sequence for free. So the way you usually add this non-reflecting stationary set is just to take conditions that are initial segments of your non-reflecting stationary set. So they're bounded subsets of gamma double plus in this case that are not stationary in their supremum, and no initial segment of them is stationary in their supremum. And you can prove that if you take a generic for this, it ends up being stationary at the top, but no initial segment is stationary. So it adds this. I'm going to put S dot, where S dot is the generic non-reflecting set added. Okay, so this is one part. So this is where the club sequence comes from. So, okay, if I can do this, so let me call this forcing S gamma double plus, because it lives on gamma double plus. So if I can do this, then I can look at the forcing S gamma double plus star A gamma double plus, and then, you know, X vector dot, where X vector dot is some club sequence added by this forcing. Okay. And then another sort of magical fact is, if I do this forcing, and then on top of this, I kill the stationarity of this set that I added here. So I'm going to write the C S dot maybe. So this is shoot a club disjoint from S dot. This forcing is just equivalent to first adding one subset to gamma double plus, and then adding many subsets to gamma. Okay, so this is quite fantastic. It's not completely unexpected though, right? Because remember what I said when I said that this forcing, this Apter-Shelah forcing, if X is, essentially disjoint, then this just more or less collapses to the Cohen forcing. Okay, but now look, if I have this stationary set here and then I shoot this club to make it non-stationary, I'm still using the old version of the Apter-Shelah thing. So now in the extension by these two, this one is just plain old Cohen forcing because the index set of this ladder system is now non-stationary, and you can prove that therefore the ladder system must be essentially disjoint, right? So this thing just collapses into this plain Cohen forcing, and these two together give you this Cohen forcing here. Okay. So now we essentially have all of the ingredients, right? So when Apter and Shelah invented this, what they were doing was they were trying to control degrees of strong compactness that you have around. So we did this with ladders of order type omega, okay? And if you look back at this sketch, this essentially told us that not just there's no measures on gamma in the extensions, there's no countably complete ultrafilters in the extension, okay? By taking ladders of longer order types, you can permit some levels of completeness of ultrafilters, but stop somewhere above. So that gives you some control over degrees of strong compactness that you have. Okay, so now we have all of the ingredients. So now just iterate. I'm going to iterate this all the way up to kappa. So, okay, well, for gamma inaccessible. Okay, and then at the end, okay, I better do the same thing at kappa also because of, reflection reasons. Kappa double plus, and do this one. Okay, and then bring kappa back, right? Okay, and if you sort of, fight your way through the argument and the forcing machinery, you'll see that altogether what this forcing did was blow to the kappa up to be kappa double plus, okay? And it killed all of the measurables below kappa using this part. And the embedding that you started with, the kappa plus 2 strong embedding, lifts to this final extension. It started off by being a kappa double plus extender. So therefore, in the extension, it now turns into a normal ultrapower that captures the entire power set of kappa plus. Okay, so this is more or less where...
You needed some fancy way of killing measurability.
Yes.
Large object.
Yes.
So then when you started doing a Google search, you found the forcing? Or Roddick knew, or you knew about this after?
No, I'm not sure how much I'm allowed to say on video. So I vaguely knew about this forcing, but Arthur had warned me in the past that the paper is quite hard to read, so I never read it very closely before this project. And now I read it quite closely, and I decided it's not that hard to read, and the forcing is quite powerful. I should say I find this forcing to be very fascinating, right? Because it gives you, I know essentially one interesting example of a forcing that kills a large cardinal and then allows the large cardinal to be resurrected, which is this Kuhnen argument where you can add a Suslin tree to kappa, and then shoot a branch to the tree, and the entire thing amounts to adding one Cohen subset to kappa. Okay, so this, it's a quite nice argument. It kills weak compactness in the middle, and then at the end you bring back.
A non-reflecting set and then killing is another very standard.
Right.
Or square principles.
Or square principles. Okay. There's more things that I don't know apparently, right? But this is another example of something like this, where, well, it's unclear to me. So, for example, right? So, adding a non-reflecting set will also kill weak compactness in the intermediate model, right? I'm not actually sure whether after you do this, okay, the measurability of kappa is killed. Is the weak compactness of kappa killed? It's unclear to me right now, right? So it might give you some finer control. Okay, so I'm almost done. I want to give you one more result because I think it's quite interesting, and it leads into a question that I want to end with. So. Okay, we managed to prove that the capturing property does not have any direct implications for the size of kappa in V, right? Consistency-wise, it does. In an inner model, kappa will be quite large, but in V, it might just be the least measurable. But you could maybe hope to extract at least something else from the capturing property, right? So, for example, a thing that you might hope for is if I have if I have CP kappa kappa plus, okay, so CP kappa kappa plus, this means that kappa has something that you could call a fat normal measure, right? There's a normal measure that captures the entire power set of kappa plus, okay? Okay, and what you might think is that, okay, there's a fat measure, but maybe there are at least some thin measures around as well, okay? So maybe, every measurable necessarily has some thin measures, and then possibly there's a fat measure floating around as well, okay? And what I mean by a thin measure is just something that doesn't capture, okay? So maybe there are always thin measures. Okay. And the point is that this is not true. So let's see. Okay, I'm going to phrase this in a slightly weird way. If there is a model with a kappa plus 2 strong kappa, then there is a model with CP kappa kappa plus, and kappa has a unique normal measure. Right? So the unique part is the interesting bit here, right? So it has a fat measure that witnesses the capturing property, and there's no other measures. Well, no other normal measures. Okay? So this is quite interesting. The gap in my knowledge here right now is how do you combine this result with making kappa the least measurable? Right? So the question is it consistent that three things, right? CP kappa kappa plus, kappa is least measurable, kappa has a unique normal measure. Okay. Yeah. To get something like this, I think the idea should be is to take this after-Echelon machinery that you have, and instead of making it based on Cohen forcing, right, the working parts of this A forcing were Cohen conditions, somehow make them be Sachs conditions, or products of Sachs conditions, and then maybe something like that could be made to work.
Here you're using what I did with Magador?
Yes. So in fact, it's the exact same model. Right? In that model, you get the capturing property.
This very subtle after Shalaf using sex.
Yes. Yes. Okay. So this is
Ambitious.
that's, well, I don't know. I'm optimistic, I have to say. There's a good candidate for what the forcing should be. It's just a matter of proving that it has a particular property. Well, yeah, it's a matter of yeah. Essentially, what the hard part is proving that if you do something like this, where this A is a putative Sachs version of this A, that this entire thing turns into, maybe a Cohen set and, a large product of Sachs's, which seems plausible, but who knows? But yeah, so I think I'll just end here. I'm over time anyway, so.
Very nice questions. Neil.
Are there any generalizations of the capture property to cardinals defined by extenders? Does anything change if you look at analyzing it sequentially, or when we've got different iterations going on?
I see. Well, I have to say I haven't looked at this very closely at all. Capturing by normal measures seemed like an interesting problem because in a sense, it's the minimal structure that you could try to capture in, right? As soon as you have stronger extenders going on, you're going to get more capturing for free, right? But you could definitely ask the question, what does it mean for an extender of some particular length to capture more sets than you would expect it to? Yeah, that's definitely a natural next step that you could take.
I mean, along those lines, you had kappa the least measurable.
Mm-hmm.
Maybe you want the least measurable of order 1.
Right.
I mean, there's lots of them.
There's you can put whatever parameter you want in here. And
think of all the papers you could write.
Definitely, yeah. There's only so many hours in a day, though.
Well, thank you very much.